I'm just going to start by saying these problems give me a lot of anxiety.
And not.
Teleprompter,
yeah.
Still
Right.
sort of face the right
Okay.
I don't know what to say about it, just that I don't like it.
That's good.
Maybe the glove's an important part of it. That 1 equals the square root of 1, which equals -1. Okay, something here is not right.
Well, when I'm looking at this proof, the first issue I see is in the first line, because when I do the square root, I have to remember that it's plus or minus 1 is the square root of 1. So I definitely feel like the problem is going from step 2 to step 3, or maybe everything between step 1 and step 3.
Taking a square root can be multi-valued, right? Like how when you have a real number, you got the positive square root and you got the negative square root. But the issue is that when you have complex numbers like this, things become even freakier. And so when you take the square root of a complex number, the issue is what angle are you going to accept as like the output of your function?
That's it. You can't break a square root like that.
Why not?
You can pull a square out, but this is not pulling a square out. Like this is just bad.
Good.
Right, so we're doing this step and we're breaking this up. And when you think about the square root of 1, you can think about it as either the positive or the negative root. And here we're kind of choosing, we're almost using both of them in order to say that this gives us -1 in the end.
Squared is 1, and 1 squared is 1. So the square root of 1, well, this is plus or minus 1. So there are two different ways of doing this that give us two different answers. And so I think what this step is really doing is this is saying 1 squared underneath the square root, but then this is also using the fact that this is like the minus square root of 1, right, collectively inside of it. So this is like, minus square root of 1 times minus square root of 1, right, which is -1. So this is using like the two different definedness of the square root and try to make them inverse of each other. Alright, so this is the second problem.
So everything, I want to say that everything that we have from the glove really does help. I want to say that everything we have like here is technically correct.
Remember trying to say equals. Oh, how do you even do that? That's funny.
Oh yeah, because the number of summands isn't fixed, taking the derivative of something that isn't fixed like that, you're going to end up getting some quantity of x out of it, which is probably, there's probably a way where if you account for that, you can get the right derivative in the end, maybe.
Yeah, so I think the trick here is partly with the setup, and then partly with like from here to here. And so what's actually buried in the setup is that this sum is dependent on x, right? And so like d dx of like ax plus bx, whatever, something like this, right? For this to be like a plus b, this is only like well defined when the sum doesn't depend on x, right? And so I think this is similar to why you can't use the power rule on this function. I think it's like a pretty similar argument, except instead of multiplication, you're like exchanging addition.
Okay, so for me, when I think about a derivative, it's the rate of change of this function as you change x, right? It's how much your output values change. And I feel like splitting x squared up into into this sum of x's and then trying to take the derivative like that doesn't represent the fact that if you're increasing x, you have a bigger sum here. So the way we're splitting up this x squared is not capturing the fact that this really grows when this right-hand side is going to grow when x grows, and we're not capturing that by just adding a sum of x's.
Subtracting the integral from both sides, 1 equals 0. Okay.
I don't remember integration by parts in my head, so I have to write it down.
Let's see, so we're going to expect this thing on the right. If we forget about the integration by parts for a second, we should expect that on the right to be what? Like natural log of the absolute value of f plus a constant. So we got natural log of the absolute value of f plus a constant.
Where's the plus? When we take this integral on the right-hand side here, we can have any constant added in. So it doesn't make sense to think about like whether the left side and the right side differ by a constant, because our integrals can always differ by a constant. So.
Oh, you didn't add plus c. You gotta add plus c. And so this is now plus c, and then this means 1 equals c. So for this to be true, like,
Why do you have to have plus c?
because all antiderivatives differ by a constant.
Yeah, and then c is 1, which exciting.
Good.
Right, but we have no guarantee that this constant here, which we'll call c1, and this constant there, which we call c2, there's no guarantee that those things have to be the same. And so the fact that you do the process one way on the left here, and you get one kind of constant, and you do the process another way on the right and get a different kind of constant, that isn't going to mess anything up. And so because of that, we can't just do this, do the subtraction in the end in the same way.
We can
I
get
guess
you
I'm giving
started
too
on-
much faith to the person writing these.
That is true. They are false proofs after all.